When I started planning this series, I was sure of one thing, that I wanted, of course, expert speakers and somebody, an expert, to talk about time travel. And I was very lucky to find Chris Taylor, who didn't hesitate to offer to give a talk. Dr. Taylor has been a professor of physics and astronomy at Sacramento State for 10 years. He has been a researcher at universities in Massachusetts, in Germany, and Canada, and was a student of astrophysics at Michigan State University and the University of Minnesota, where he earned his PhD in 1995. Ladies and gentlemen, please welcome Chris Taylor.
All right, thanks. I'm glad to be here. I'm just remembering this summer when Stephanie reminded me that I agreed to give the talk in September. I thought, maybe I should reread Outlander. It's been a while. I read it when it first came out. So I requested it from the library. I live right next to the Rancho Cordova branch. And I was horrified to learn that all the copies were checked out and that there's a very big, long waiting list. And so I actually didn't get the copy of the book until the beginning of August. And that's right when the semester started, so I didn't actually have a chance to read it before I came here. So I feel horrible. So maybe I thought to make up for that, I might give my talk in a Scottish accent. That wouldn't go so good. So I decided that in honor of Papa Day, I would give my talk in Westron instead. So, all right. So, I'm a professor of astronomy at Sac State, and so I'm here to talk to you guys a little bit about how time travel might really work. And that's kind of misleading because we don't think it actually would work, at least not, backwards. And going forward is easy. We're doing it right now. But going backwards in time, we don't really think it would work, but it turns out that you can't prove it doesn't work. And so that's what we're going to talk about mostly today. So. Now, here's sort of the popular conception of how time travel works. This is a publicity still from the time travel movie from the 50s, I think, when this movie came out. Is an actor Rod Taylor? Yeah. Right, so no relation. And there's some device here, and the big wheel spins, and the scientist, he wasn't evil, but he was some kind of laugh and maniacal laugh, and then all of a sudden they're whisked back and forth in time where they want to go. And that, of course, is a 50s interpretation of a movie from 2 centuries ago now, because we're in the 21st century. Here's a slightly more modern version. Of the same basic idea, a device which can whisk you back and forward in time. You just input the date you want to go to, and boom, you're there. Along with, I guess, what most people think scientists look like. That's how they always see it in Hollywood, right? Every movie, it's either some guy in a white lab coat who's crazy, or some evil scientist doing an evil scientist laughs and learn. And that there is the grad student, I guess. That was me. Time travel itself is not thought to be possible by the vast majority of the scientific community, but like I said, we haven't proven that it can happen. The laws of physics we understand do not exclude it, so we have to at least be open to the possibility of it. Okay, there we go. However, this is one of those ideas that keeps getting brought up from time to time, and not just by crackpots and weirdos, but by regular scientists as well, who are examining a piece of physics, normally it's something related to Einstein's theory of relativity, which is what we'll spend a lot of time on today. And they look at some aspect of it and say, maybe this could be used to make a time machine, and they write a research paper on it. It appears in one of the legitimate scientific journals. Everyone reads it, says, hey, that's awesome, and they go on to their regular lives and never talk about it again. So that's what we're going to talk about here, some of those ideas. Some of them are technically possible, or I should say technically not impossible, there's a difference, but highly likely, and some other ones are less unlikely. So we'll talk about both. So if we want to talk about going backwards in time, which of course is, I guess, fun because all kinds of cool stuff is backwards in time, like dinosaurs and kilt-wearing Scotsmen and so forth. Well, I guess they're still out there today, right? Just not as many numbers. Time travel going backwards generally relies upon one of 2 ideas. One is the idea of tachyons, which are a theoretical particle in physics. So particles in physics, you've got atoms, right, which are made of protons, neutrons, and electrons. This is all stuff you learn in chemistry class. It turns out that protons and neutrons can be divided into smaller particles, and there's all kinds of smaller particles beneath that. And so there's probably about 30 different kinds of particles that particle physicists study. And then they have these gigantic colliders, like the Large Hadron Collider, where it's sort of supposed to kill us all by making a black hole and sucking the Earth in, which didn't happen, by the way, so relax. Tachyons is one particle like that. The difference, however, is that all those other kind of particles that make the Large Hadron Collider have actually been seen. Tachyons have never been seen before. They remain strictly a theoretical possibility. And one of the reasons why they haven't been seen is they actually travel faster than the speed of light. That's the basic idea behind tachyons. And so, if such a particle were to exist, that allows a way you can have time travel. And one possibility is you could build a car, for example, out of tachyons, which would move faster than the speed of light. That would be, so implausible that's something we were talking about. But people have given a lot of thought to the idea of using tachyons to send kind of Morse code messages back in time. In fact, there's a book called Timescape by Greg Benford, who's an astrophysicist at UC Irvine, I think. And it deals with a group of scientists in, I think it's 2020 or something, so we're coming up soon, there are events in the past if we want to. But a group of scientists who use tachyons to send messages back in time to a group of scientists in the 60s to tell them to stop polluting the Earth because we're all going to die in the 2020s from all the pollution. So, and that was the subject of that book. It dealt with what happens if you change a timeline, and is there a paradox involved, and all kinds of stuff like that. We'll mention that stuff a little bit later too. But in a sense, tachyons are kind of unsatisfying because you really want to go backwards in time. You don't want to just send messages. You want to go back and see dinosaurs. You don't want to go back and send messages to dinosaurs that never understand. Right? So we'll talk about tachyons, but they're kind of unsatisfying. Then we'll focus mostly on unusual geometries of space-time. And that is that Einstein's theory of relativity describes the universe as having 4 dimensions. The usual ones. I'll stand over here for a second. Up, down, side to side, right? Front to back. Those are the 3 that we're used to. And then there's time, which is a 4th dimension. And all 4 of those are subject to being curved or bent in various ways. And the idea of time travel through relativity is that if you bend the fabric of the universe in such a way, you could travel in a certain direction and come back to your starting point before you left. If the curvature of the universe is right. It's kind of like taking a shortcut through time. Okay? So we'll talk about how that might be possible. And then finally, I'll say a few words about the grandfather paradox. The idea that what would happen if you went back in time and, for example, killed your ancestors, either deliberately or by accident. What would happen to you? Because if they were never around to have your parents, how would you be born and able to go back in time to kill them, right? So it's a paradox. And we'll talk about the implications of that a little bit also. So, tachyons. This is if you get this, you're a physics nerd, let me just say that. So I wouldn't laugh, it's kind of admitting a vice there. So the bartender says, we don't serve tachyons here, and then the tachyon walks into the bar. And that's actually how it would happen, because since tachyons move faster than the speed of light, the tachyon will actually appear in a location before you see it coming, because the vision of you seeing it is through light rays, which, in the tachyon itself is outrunning the speed of light. So that actually would be what happened. And that's that same property that makes them useful, potentially, for sending signals back in time. We can use them to send signals back in time because they would arrive in time in the past before we had progressed forward to the time to which they were sent. So it's kind of like a loop in time. And like I said, this is, technically speaking, time travel. If they exist, you could send information backwards in time. You could send lottery numbers back to your past self so you could win the Powerball. I keep looking for messages to appear in my bureau at home with the numbers and never do. So obviously I don't invent tachyons in the future. Because that was the first thing I'd do if I did. So that's helpful. But again, it's not really what we're talking about when we mean time travel. You're not physically moving yourself back in time to participate in kind of cool events. And like I mentioned, this is the book right here. Gregory Benford wrote this novel about it. And in that novel, the scientists actually have to deal with the grandfather paradox because they are motivated in the year 2020, or whenever it is, to send messages backwards in time because the Earth is becoming so polluted it's almost impossible to live on. If they're successful, however, and they get their past counterparts to change the future, then they will never invent time travel or tachyons signaling because they won't need it to save themselves. So it's almost like you can't actually change the future because by changing it, you prevent yourself from being around to change it in the first place. And so he talks about various different ways you can sort of fudge that around. In the book ends in a very positive way. People don't all die of pollution, so it's good. However, and this is kind of the bummer part, no tachyons have ever been discovered. They remain even today strictly a theoretical idea, and as far as we can tell, they're not for real. Okay. And by the way, if Einstein is right, and one of the things that Einstein says in theory of relativity is that nothing moves faster than the speed of light, then there aren't any tachyons. So far, every time we checked, Einstein's only been right. Kind of a bummer, actually. All right. So, and there he is, Einstein, in theory of relativity. So, if you want to talk about moving backwards in time physically, either yourself or moving artifacts or whatever, then the theory of relativity is your best shot. Okay, that is the one area of physics which allows for the possibility of time travel, although it doesn't say that it's possible, it just doesn't say it's impossible. Now, the theory of relativity, and there's two versions of this. There's the special relativity theory, which is the easy one, which only takes you about a year to study, to learn. And then there's the general theory of relativity, which is the more complicated one, which no one actually understands, except probably Einstein. Although everybody understands a little piece of it. Relativity itself, in either form, uses equations. They're called field equations. And with those field equations, you can describe our universe as being a four-dimensional, what's called space-time. Okay, and that's just said that way because I just want to reinforce the fact that time is a dimension, just like the other three in space. We perceive it differently, but according to the equations, it's very, very similar to just up, down, left, right, and forward and back. Now, anything that is powerful enough to alter the geometry of space-time will alter not just space, but time. And so in this diagram here, that's an example of one way in which you can alter the fabric of the universe. In the general theory of relativity, Einstein said that gravity, that is the tendency of things to fall down, gravity is created by a heavy object. This, for example, could be a star right here. And the influence that object's mass bends the universe around it in a bowl shape. And so things roll downhill in that bowl and end up attracted to the center. And so this diagram here is showing you a very heavy object, and the universe is flat, far away from the object, because the universes tend to be more or less flat. But when you get close to the object, it's curved. Now, if that curvature were to be enough, that might allow for the possibility of places in the universe where it moves in on itself and then time travel. So one way in which you could travel backwards in time is if the geometry of our universe is normally pretty flat. It's not exactly flat, it's pretty flat. Were to be severely bent in almost into a loop shape. Okay? And so one particular way of doing that is what's called a wormhole. And so this is, again, this green grid here is supposed to be the fabric of the universe and how it's, generally speaking, flat, more or less everywhere. And then if you travel along through time in the normal way, I think you start here in the bottom, you go around, and you end up in some other part of the universe. Wormholes, however, can shortcut that process. If you go through the opening of a wormhole, you could end up in a different part of the universe without having traveled the full distance to get there, so it's kind of like a shortcut. So it's effectively traveling faster than the speed of light without actually traveling faster than the speed of light, because at no point were you going faster than the speed of light, but you got a bigger distance sooner because you made a shortcut. And also because anything that changes distance, which is the three parts of space, also changes time. So some wormholes might not necessarily put you out in a different distance in the universe from where your starting point is, but a different time. So if it took, for example, a ray of light 10,000 years to make this distance, you might make it in 10 days or some other similar shorter period. And that is effectively time travel. If you make the loop sufficiently closed, you can establish the other end of the wormhole to be wherever you want it in theory. Okay. So the idea is all about bypassing the normal time and taking a shortcut to get to some other place. And you could do this going into the future as well. But if you want to go back in the past, you want to try to adjust the opening of the other side of the wormhole to be where you were, your destination. And one big thing they often forget about this is in science fiction novels is the Earth moves. I spend several weeks drilling this into my astronomy students at Sac State. The Earth goes around the sun, once a year, And the sun goes around the center of our galaxy every 250 million years. So we're never in the same place we were in space at any given time later. Which means if you build a wormhole and you say, I want to go back to the year 1945, let's say, make sure that your destination is not just 1945 where the Earth is right now, because in 1945 the Earth wasn't there yet. The Earth was someplace backwards on our orbit. And so you end up in empty space, you'll suffocate. It's not pleasant, right? So you have to make sure you adjust the coordinates that you not only go backwards in time, but you also adjust the locations that your other wormhole ends up where the Earth was in the year 1945, not where it is today. So as long as you do that, you're okay, but science fiction writers often forget that part of the thing, so I just want to mention to you guys. Now, there are several ways you could build a wormhole. One way is that if you have the two entrances, the way you go in and the way you come out, if one of them were to be accelerated to near the speed of light, moving close to the speed of light does distort the fabric of the universe. It does change those 4 dimensions of time-space. So if you did it the right way, you could, in practice, well, not in practice, in theory, you could end up with a wormhole which, due to that curvature of the universe, takes you backwards in time. Okay, that's very hard to do, however. You know, the fastest object we have that humans have ever built is the New Horizons space probe, which NASA has recently sent to Pluto. You know, poor Pluto, no longer a planet anymore, right? It was a planet when that spaceship got launched. And that is not going anywhere near the speed of light. In fact, it's taking so long to get there that if you directed that same spacecraft instead of at Pluto at the nearest star, which is Alpha Centauri, 50,000 years to get there. Okay, whereas it would take about 4 years to get there at the speed of light. So it's going way, way slower at the speed of light, and that's the fastest thing we know of we can make ourselves. So this one option here of accelerating the other end of the wormhole to a speed very close to the speed of light just isn't going to work, at least not with our current technology. The other possibility, you take the other end of the wormhole, your destination, your exit end, and put it close to an object with a very strong gravity. Now, that's a little more feasible because objects with very strong gravity occur naturally. You know, stars, for example, they're everywhere in the universe. If you want to get even stronger gravity, black holes. I mean, we have a few candidate black holes we found. We know that every galaxy out there in space, well, pretty much every galaxy, has a massive black hole. You know, it's about 3 million times the mass of our sun in their center. So we know black holes exist. So this one, at least to me, seems a little more practical. Of course, you still have the issue of, well, how do you get the other end to the black hole? Because there's not really one within close distance of the Earth. So in the end, although to my mind, the gravitational field one does seem a little more realistic, we still are nowhere near the technology level needed to make it happen. Now, that's not it, not the end of it though, however. Let's assume that you did succeed in getting such a wormhole built. Okay, so you can either accelerate the other end to the speed of light or close to it, or you put the other end near an object with a very strong gravity. Wormholes, it turns out, according to all these equations, are very delicate. They're fragile. Okay, and the very act of trying to pass through one might cause it to collapse around you, in which case you go nowhere. So the issue of even making a wormhole is totally separate from the issue. Is it even what they call traversable? Can you actually travel through it or not? And that also will be a technological hurdle we haven't really got the ability to solve yet. All right. And by the way, I forgot to tell you guys this at the beginning, but if anybody has any questions, just go ahead and stick your hand up. I'm trying to keep this pretty informal, so it's all right. Oops, all right, now, another complication is that wormholes themselves are not actual time machines. There's no machine involved. It's more like a bypass on the highway, okay? So one side effect of this is that the wormhole itself cannot go backwards in time to a point prior to which the wormhole actually existed. So if I were to wave my wand and build a wormhole right here, the furthest back you go backwards in time would be right now. You could not easily go back in time to see dinosaurs or Celtic Scotsmen or whatever. Unless there was a wormhole that was existing at that time already. We just haven't discovered it yet. So that's one issue. Time travel seems to only work from the point at which you build the time machine forward. And so anyone in the future can go back to now, but we can't go backwards any further than today. Which, you know, is again kind of a bummer if you want to see dinosaurs and stuff. Now, Stephen Hawking, here he is right here, has suggested that time travel isn't even possible. I mean, like I said, relativity doesn't say it's possible, it just says it's not impossible. Well, Stephen Hawking wants to say it's impossible. He's kind of a killjoy that way. And according to him, his argument is actually not a physics argument at all. His argument is kind of like a social argument, I guess. If time travel were possible, why don't we see time travelers right here, right now, taking pictures of us primitive people, take it back home with them and show all their friends in their futuristic slideshows, or post on, future Facebook, whatever they call it. And he said that for many years. He says he doesn't think time travel is possible because we're the people coming back in time. Now, if this restriction imposed by relativity is right, using wormhole, you couldn't go back in time to any point prior to which the wormhole was built, which means clearly the reason why we don't have tourists yet is that no wormhole's been built yet that they can use. So his objection is not actually a real objection if you buy into the whole argument of relativity. Okay, if you think that is a legit argument. So problem solved. Now we know why. Okay. Now, of course, what would the time travelers do if they came back in time, right? I mean, would you come back in time with your future technology and set up an empire and take over as primitives or whatever, or would you sort of blend in with the natives and hang out and experience pizza, which exists in the future or whatever, so there could be all kinds of social reasons why the time travelers aren't revealing themselves. I mean, maybe one of you guys is a time traveler here. If so, I would really appreciate that next Powerball number. So there's lots of social commentary. In fact, I read about this a while ago. People have set up time traveler conventions. MIT did this a few years ago. Some people called the Chrononaut Society, I think, did it in Baltimore a few years before that, where they advertise in a permanent way, some kind of permanent plaque or something that will last thousands of years in the future. Time Traveler Convention in Boston on March 6th of 2009, just so any time travelers can come back and visit, because they have people waiting for them, and no one showed up. So again, either it's not possible, or they don't want to reveal themselves, or who wants to be treated like a weirdo, going back in time, right?
I know. I just want to say hi.
Okay. All right.
Just to let y'all know I support you with everything that you're doing.
Okay. Okay. So now this whole wormhole thing is the main possibility for how we think that time travel would work. It's possible at all. But there are some other slightly less plausible ways. I mean, if you can get less plausible wormholes, it's kind of really out there now. But one person suggested that if you had a cylinder that was infinitely long, and so you can see we're going to get into problems right here, because how can you possibly have anything that's infinitely long? But physics is full of this stuff. Everything is infinitely long, or infinitely big, or infinitely far away, whatever. And it just makes the math easier, right, in certain ways. So the equations were solved for a cylinder. Think a paper towel tube that extends at both ends off to infinity, never stops, that spins at almost the speed of light. Theoretically, if you were to travel close enough to that, it's called a titular cylinder, after the guy who thought the idea up, you would travel in time. Okay, that spinning has the same effect as gravity in terms of warping the universe. Now, that opens up like a whole bunch of other problems, though, because there's no such thing as infinite anything, except emptiness, I guess. So you can't have an infinite cylinder, and if you did have an infinite cylinder, it would weigh infinity, and so how would you make it spin? Where's the energy going to come from to spin it? And if it's not infinite, does the process even work? And Tipler actually said that he thought it would work, but he wasn't able to prove it mathematically. So it's kind of a one possible way, but we don't know for sure. And the other one is the use of cosmic strings. Now, cosmic strings are kind of like fractures in the fabric of the universe, in space-time. And I've got a picture of a crystal here because they form in an analogous way as to fractures inside crystals, or maybe when ice freezes, it doesn't freeze uniformly smoothly. There's little cracks inside the ice. Not because you stepped on it, but because it just froze that way. That same process that causes cracks to form inside crystalline structures is thought to take place when our universe is forming during the Big Bang. And so the areas where the fabric of the universe is not smooth but is cracked or disjointed, that's called a cosmic string. And again, the universe is 3 dimensions plus time. So if you're cracking in 3 dimensions and causing it to be unusual, you're also doing things with time as well. So it's also possible that you could make a time machine based on having it the way a cosmic string distorts the universe. That would work. Of course, there's a big problem. Again, cosmic strings are only theoretical, and we never actually observed one. And we don't think we could possibly make one, so we'd have to find one someplace and either do our time traveling out there, wherever it happens to be, or somehow drag it to space. Now, I know there's these guys who are planning on, at NASA, are planning on lassoing asteroids and dragging them over the Earth's orbit to mine them. So maybe you'll have something for lots of synchronic strings in the future, I don't know. But right now it seems pretty hard to do. So these two are not, I mean, as much as time travel is taken seriously by any scientist, these are some of the less serious possibilities. And of course, you have this issue right here. You go back in time and oops, sorry, you just killed your own ancestors and now you don't exist. That's the classic grandfather paradox, right? It doesn't have to be necessarily exactly like this. You could go back in time even further. There's a Ray Bradbury story, right? It's called The Call of Thunder or The Sound of Thunder, where they go back in time to the dinosaur era and they make a change. The tourists make a change that leads to humans not ever evolving. So any kind of change that you caused to happen in the past could change the sequence of events that led up to not just you. I mean, here it's just you, I guess. That's your grandpa, but it could be anything in the universe or on the Earth. So if you're going to time travel, you sort of have to be aware of that, and that was kind of the whole point of the Back to the Future movies, right? Where Marty got this whole edible thing with his mom back in the past. Yeah, not a good way to go about having a good future. So what happens if you go back in time? Well, again, Stephen Hawking, being the killjoy that he is, has conjectured that the fact that you don't want to have a paradox, because how could you have prevented yourself from existing? Because if you make yourself not exist, how did you exist to make yourself not exist? So it just goes on forever, that loop of paradox. He says, well, that very fact that you could have a paradox means that time travel is impossible because nature won't allow a paradox to happen. Okay? Which again seems kind of like a lame argument to me. I mean, you can't prove it mathematically that way. And so one possibility is what's called parallel universes or parallel timelines. Okay, and this is what people who think that paradoxes can be resolved often point to. So here's the grandfather. Your father's born. Okay, you're born here. You travel back in time. You actually kill your grandfather, or maybe you do it on purpose. I don't know. People have bad families sometimes, right? Grandfather dies now, but now this is right here. Father never born, you never born. That's a brand new timeline. It could be a parallel universe that either never existed before, and you created it, and the universe made this happen to prevent a paradox from happening, because in this timeline your grandfather's still fine. So both happen. You get to have both ways. Or maybe this all the way, now the time machine would take you back in time to a separate universe where your grandfather did die. It was going to happen anyway, and it just took you there for your time travel, so that the sequence of events unfolds naturally. So that's how people tend to resolve these. And there's a whole genre of science fiction novels that revolves around parallel universes and he travel back and forth and so forth. Yeah?
It sounds like fate.
I guess it could be fate. Yeah, I mean, you go back in time. Fate, I guess, is just a name for something you don't understand yet. Yeah. Okay. So, yeah, actually, there's a really good series of novels by an author I'm fond of called Charles Stross, which hypothesizes a complete set of parallel universes. And there's this one family which discovered a way of traveling back and forth, and they set up a black economy among different universes, trafficking in things that are rare in one universe but not rare in the other one, and making a buttload of money along the way. It's really not so much a technology novel as it is an economics novel. So if parallel universes were real, how would you exploit them to get rich? Now, going forward in time has some different approaches, although I will say tachyons, moving faster than light, can move into the future, so that would still work. And wormholes ought to work also. You should be able to go forward in time if you go through a wormhole out to the other end. But there are other ways to go forward in the future that don't really require wormholes or tachyons or anything like that, so it's a slightly different proposition. Number one, of course, and I mentioned this at the very beginning, we're doing it right now. I mean, you are now 40 minutes older than when I started. You can't have those 40 minutes back, by the way, sorry. So we're traveling in time anyway. But the question is, can you slow it down so that for you a smaller period of time passes, whereas for everybody else a longer period of time passes? Then from your point of view, it would seem as though you traveled in time to a future point. Now I should say that all these things I'm going to talk about now are irrevocable. You can't go back if you do them. Okay? So in one sense, hibernation or suspended animation is like that. And isn't that the Woody Allen movie Sleeper, where he gets in suspended animation and wakes up in the future and he was actually existing for that whole time frame. Didn't cease to exist in his time and then magically appear in the future. He was there all along, he was just asleep. So in a sense, it's not really time travel like we're talking about, but it has the same effect in the end, okay? So you go forward, you travel in time, and all of a sudden you're awake. And then, of course, you can't go back. Now, the theory of relativity also has ways that you can accomplish the same thing without actually having to, do, I don't know, sleep drugs, whatever it is they do, sleep, I forget, they froze them or something. And the idea from theory of relativity is time dilation. This is a phrase that means the slowing down of time. And there are certain circumstances which time slows down, okay? And one of those circumstances is if you are moving at a very high speed, and this gets stronger the closer you move to the speed of light. And so this diagram right here is going to show you, this is a clock, let's say here on the Earth, and it's moving whatever speed the Earth moves around the sun, pretty slow, okay? Right here is a clock on a spaceship that's traveling at 87% the speed of light, so really fast. That's way faster than we can currently go right now. And what happens is that in the 20 minutes since noon, the clock on the spaceship only went 10 minutes or so. So time passed at half the rate for people who were on the spaceship as it did people who were here on the Earth. And this leads to the famous twin paradox, where a space traveler comes back to the Earth after traveling close to the speed of light for many years, and they're 35, they come back when they're 40, and their identical twin is now 80 because they were gone so long, and they age slower. And the twin paradox, by the way, is like the favorite thing to talk about when you're a physics student. Because when the professor first brings it up, everybody goes, ooh, what about this, what about that? And I remember one guy in my physics class who said, well, what if the twins are born on an aircraft carrier and the spaceship swoops down and the doctor throws one of the twins on the spaceship? Because the whole thing with the twin paradox is you can sort of resolve it by realizing the fact that spaceships have to slow down to get to planets to stop and start again. So the whole idea was if you avoid the slowing down, stopping, you can outpull the twin paradox, which is crazy. I mean, that was like in 1986, and I still remember it. That session, that's how crazy it was. So anyway, so that's one way you can do it. The other way, and this is sometimes familiar because this is also how we make wormholes, right? Being close to an object with a very strong gravitational field. Okay, so either one of these will work. Now I will point out that both of these have been proven. Okay, so here, this is not hypothetical, maybe it's kind of good science, not. In number one, number two, if you want to go forward in time faster than everybody else, it's just a matter of technology. The science is there, it's just the engineers have failed us. Sorry for an engineer. All right, so traveling at high speeds does cause time to slow down for the traveler relative to non-moving observers. So for example, if you went on a 1 week trip out in space, maybe a 3-hour cruise, you come back to the Earth, thank you. Some people aren't there got the reference. And 1,000 years have passed on the Earth. Okay, so you travel in time. For you, it was just a short period of time, but 1,000 years went by on the Earth. When you get back to the Earth, you're stuck. Okay, this kind of time travel only works going forward. So I don't recommend it unless you don't have any friends and family. Okay? But this is the kind of thing that people often talk about in science fiction novels because you can sort of, take this water bottle, bury it someplace, come back 1,000 years later, and it's an artifact that's worth $1 million because it's a rare 21st century artifact and you're out in the 30th century, right? So that's a common theme you'll see in time travel stories and novels is, hiding objects, leaving them for yourself to find the future and getting rich on that. The other way you can travel in the future is through gravitational fields, again, and this actually has been proven by using GPS satellites. So we are here on the Earth, we're pretty close to the bottom as you can get on the Earth, that being a hole in the center. GPS satellites are further out, so they are experiencing less of the Earth's gravity than we do, which means we have a stronger gravitational field right where we are. And according to relativity, our clocks should move at a faster speed than identical clocks on those GPS satellites. And in fact, when they first turned on the GPS satellites, in order to make them work, they had to actually take that into account. They had to calculate how much time dilation the Earth is experiencing down here at ground level compared to the GPS satellites. Otherwise, you wouldn't get the right coordinates on your GPS when you were trying to figure out where you are on the Earth and you get lost. So again, this is proven science. We know this is real. The question is, of course, how do you get to a stronger gravitational field to make it significant? The difference between us and GPS satellites is a fraction of a nanosecond. it's not really important unless you're trying to figure out where you are on the surface of the Earth to the accuracy of a meter or so. Yeah.
How does time actually slow down by traveling at high rates of speed? I just can't get that.
Yeah, that's also one of those things that we talked about in that class in 1986. And it's really hard to understand because it doesn't make sense to our normal experience, right? The math is pretty clear. You know, if you take calculus, you can do the math that will demonstrate to you that yes, time will slow down. But we don't have a good analog experience in our lives to sort of help us visualize it. I mean, the only thing I can say is I get back to that whole, the shape of the universe is being warped a little bit. So think of a tablecloth with wrinkles in it. And so you would have to travel along the wrinkles if you're in the universe going normally, but going at a speed close to speed of light is kind of like traveling through the wrinkles and coming out the other side. So less time took place for you than it did for the person who went up and down like that. Now, having said that, that's a totally terrible analogy, but it's kind of like the best I can come up with.
Thank you.
Yep. Okay.
Oh, how about, was it Mickelson Morley? They shot the light across from Mount Wilson?
Yes.
And back, and then that way and back?
Yeah, so the
Showed
Michelson,
the difference in speed.
yeah, so the original Michelson-Morley experiment was to prove there's no ether in the universe, there's no medium in the universe. But later experiments have been modified to test relativity. And that is one of the ways you can do it, yeah.
I got a question for you.
Yeah.
What makes photons move?
Uh,
In the very start of light,
yeah.
what makes them go?
Well, photons are in quantum physics considered to be particles of energy, and they have a certain amount of momentum, and anything that has momentum will move. And so that's the reason why, and then that just says, okay, why do they have momentum? Because I just changed it, why they have velocity to why they have momentum. And that is just, I mean, the answer to that question gets at sort of like the Higgs boson, because these small subatomic particles actually contain in them the reasons why matter has mass, or why electrons have electric charge. And it's all about what mixture of basic fundamental particles existed when the universe was first formed during the Big Bang, and how they mix together to make the rest of the particles of the universe. And so photons are just those kinds of particles that formed in those very early days that had the right combination of stuff.
Showing my flashlight, I got a beam of light going.
Right?
In 1,000 years, it's still going the same way, the same exact space.
Yeah, yeah, and unless a screen blocks it or the ceiling blocks it. Yeah, very light will travel forever. It will probably travel in a straight line unless it gets close to an object with very high gravity. You know, objects with high gravity will bend the ray of light.
You ever thought that maybe they repel each other and that's why they move? If they did, they would repel at a continually longer distance.
That's getting out of my area of expertise. I mean, not that my area of expertise is time travel by any means, but so I do not know the appropriate reasons why that's not the case. Although off the top of my head, we know of the 4 basic forces: gravity, electricity, magnetism is one, strong nuclear force, weak nuclear force, and photons, as rays of light, do not have the right properties to be repelled by each other according to those 4 forces. So if what you're saying is true, that would imply that there's another force that we haven't heard of yet. Which, that could be right. I don't know. But, to be honest, I really don't know the answer to your question. So, I really can't tell you.
If it did, the wavelengths would get longer as you travel.
Yeah. That's true, I think.
And we may not have any full universe.
All right. Back to time travel here. This diagram shows you how the shape of the universe curves around the black hole. A black hole, of course, is an object which has gravity so powerful that not even rays of light can escape from it. This is sort of the ultimate in terms of how strong gravity can get. It only happens, that powerful gravity when you get very close to the black hole. So you see out here, this grid here is supposed to indicate a flatness of space, because space is generally pretty flat, like I said. But when you get close into the black hole there, it starts to bend and curve. Now, it's not just space, our 3 dimensions that are bending and curving, it's also time. And the effect of that is to have time pass more slowly. This is why I just told you about the GPS satellites, only it's that idea on steroids, because the curvature caused by black holes is much more powerful than the curvature caused by a wimpy object like the Earth.
Yeah, but it would be incredibly dangerous.
Yes,
If you
yeah,
suck into it.
yeah.
You try to get faster, but that would be more
Yeah,
risky.
yeah, so the key, of course, to time travel at a black hole is to not fall into a black hole, because you don't get out, right? But also, you know, if you go in a certain distance, you have to make sure you've got enough fuel to get back out again, obviously, too.
Or to fight the gravity.
Yeah, exactly, yeah. But assuming you can do that, which is by no means assured, and that's again where the engineers have failed us, not me, but the engineers, right? If you go in close, hang out for a couple days, and are able to come back out somehow, time will pass far more slowly for you than it would have for everybody back on the Earth. So again, that's how you do it, subject to all these technical limitations of, you know, we don't have spaceships that can get us to a black hole, we don't know we can get close enough without falling in, you know, but that's all technology problems. The basic physics works. I mean, the fact that GPS satellites, you know, we've all got GPSs in our phones these days. The fact that this works, and you don't get lost in the way the library, which is how I got here today. So the fact that I'm here means time travel is possible, at least going forward anyway. Okay. Time travel in general is iffy, you know, for lots of reasons. Even in the cases where the theory says it might work, it's really, well, we can't prove that it doesn't work. But even in situations where we know it's possible, like I just said, going forward at accelerated rates, even then, the technology is way beyond our ability to handle right now. So, however, time travel in the future is definitely possible. And once we have the technology, we might be able to do it. So I'm here now to ask you, if anybody volunteering to do the first experiment. You know, it's at that. Those guys in Holland who took out volunteers for the one-way trip to Mars. Anyone want a one-way trip to the year 3013? That'd be awesome. All right, and that's it. Thanks. So we have time for questions? Yeah, okay. Go for it.
Okay, I have a question. You said you can't go backwards because what you would go back to wasn't there. You can go
Yeah.
forward, but if you go forward, let's just use the wormhole thing.
Right.
If you go forward, you could then go back because what was there is there.
Yes, so that depends on where the exit of the wormhole is, but yeah, that's right. And that's why the wormholes are so tricky, because even going forward, you gotta make sure that the other end of the wormhole is where the Earth is gonna be.
Right.
Or else it's not space too.
But since you already did it, you know it's there. So maybe the people who were going back really were forward, went forward and then went back.
Well, if you can go back, you should be able to go forward too, so yeah, that's
No, I
possible.
mean, you say you can't go back, but so, let's say you went forward
Uh-huh.
and then went back.
Oh, I see
You know
what you're
the
saying.
back
You
is
know where
there
it is,
because
yeah.
you went forward.
Yeah, and that, of course, and that's a situation where you know where the other end is gonna be, because you
Right.
made it there in the first place, yeah. As long as you're sure where the other end of the tunnel is gonna be,
It being in the future.
you're gonna
you
be
may
okay.
alter
Yeah.
Paths you wanna go back to.
Yeah, I mean,
Inadvertently.
yeah, I mean, it's things they
How
sort
to
of
avoid
wave
doing
with
that.
Doctor Who. You know, in Doctor Who, the TARDIS can do both space and time, right?
Right.
That's in the name of the device itself. So they sort of said, oh, not worry about that because it moves through space too. But, you know, with the wormhole, you need to know where the other end of the wormhole is going before you jump through. Otherwise, it could be very unpleasant on the other side. Yeah?
Have you ever heard of was a '60s episode, you know, of a series called The Time Tunnel?
I've heard of the time tunnel. I've never watched any of the episodes though.
Yeah, well, it's actually where they had a machine, and what they did, these two guys, one guy experimented with it. They were trying to, you know, build this time tunnel, right? The one guy decided, you know, he sunk into the base where it was at, and he put the switches on and went in. And then they sent the other guy in to go after him. And what they did was they were able to go back in time or in the future, and they would go back to like different things. Like for instance, they went back to the Titanic.
Mm-hmm.
They were on the Titanic, and they were trying to convince the captain to turn back because of the glacier that was coming.
Right.
And he got locked up, right? Then they sent the other guy in, you know, to try to rescue him, you know.
Mhm.
And then at the end, when the boat was going down, they froze them, and then they sent them on somewhere else. Do you think it's possible that maybe if you were able to travel back in time, it would be like different worlds that's just outside the universe or something? Because it wouldn't seem like it would be anywhere in the universe if you did go back.
Yeah, and that's kind of what this little diagram here is going for. If you did go back in time and cause an actual change in the timeline,
Yeah.
a lot of people think that actually means that you either went to a different universe where the timeline was different to begin with,
Yeah.
or else you caused a brand new universe to form when you change the timeline.
Right.
And now there's two, the one where you came from, which you can never go back to, and the one you're in now going forward, which is like this. So yeah, that is an idea which, you know, physicists, this is the kind of thing they talk about when they get drunk at conventions. And you know, they're studying the hotel bar, and they're writing equations with back of napkins. But yeah, it's this thing that.
I personally don't think that if you were able to go back in time,
Uh-huh.
I don't think that you would actually be able to change something that is going to happen. Because
Right.
it's going to happen anyway. You know,
Yeah.
you know, people won't even believe you.
Right.
You know, even if you tell them, I'm from the future and I know this is going to happen, you know, they might lock you up in a mental institution or something.
Yeah. Wasn't that?
You know, what happened on the Titanic where they locked the guy up. You
Yeah.
know? The other thing it is going into the future. What would happen if you were able to go into the future, and let's say you went into a time period you didn't even know of, where the Earth is destroyed,
Yeah.
and you would die with it too, and you wouldn't be able to come back, right?
Yeah. Well, and yeah, that's exactly right. That's why you don't want to go forward in the future if you can help it.
You don't know what's
Yeah.
ahead.
Yeah, exactly. You might go to the year 3013 and find out that you know, the cockroaches really have taken over. Yeah.
The whole Earth is destroyed
Yeah.
or something, you know.
That's right.
Or it's such peril
Uh-huh.
that, you know, let's just say there is, you know, some kind of ecological disaster,
Right.
And you're stuck right in the middle of it,
Yeah.
you know, I mean, then you're gonna go with everyone else, you know.
Yeah. Okay. You got a question? Yeah.
Yeah, I'm a big Gene Roddenberry fan, because
Uh-huh.
I consulted with Az one, so
Right.
those guys. But, you know, he had a really good episode in the Gen 2 where there was like a 25 millisecond offset in time. So people were actually there, but you couldn't see them.
Oh, yeah?
Because they were either like a quarter of a second
Oh,
behind
yeah.
or ahead.
Yeah, wasn't it like Jordy? Was
Yeah.
Yeah, I remember that one.
And that's fascinating. I mean, since time is a variable,
Yeah.
it's almost kind of plausible if you could twist time.
Yeah. I mean, I don't really see, yeah, and that was kind of like, that seemed to kind of like be an alternate dimension almost, but when that was very close to our own, so you can still see what's going on or something.
Yeah, that's right, yeah.
So,
Seemed like
Uh,
right.
Just a comment. I think it would be really great to go back in time to correct the records, to get the lies,
Yeah,
et cetera, et cetera.
yeah,
If you can get back there, just
Yeah.
maybe take the camcorder.
right. Yeah, well, it's interesting that you mention that because there's a series of novels by Connie Willis, a very distinguished science fiction author, where that happens. Time travel has been invented, and it's used mostly by historians who travel backwards in time to record events, but they're instructed to be very careful not to change anything. And for example, the first book in the series is called Doomsday Book, which is after the similarly titled book that was written in England in the Middle Ages. And so the main character is a history student, a PhD student, who goes back in time to observe people dying during the Black Death in England. And she's told, you know, don't help anybody because you might change the future. If you save somebody, you're supposed to die. And then she gets sick of something different because she had inoculations, so she wouldn't get it. And then they lose her. They don't know where she is. They can't come back and bring her to the future again. So so that whole series of books, and they sent people back to World War II to observe what's going on there. Yeah, so it's exactly like what you just said, with the complications mixed in of not having to change the future. Yeah.
Well, speaking of Connie Willis and the Titanic, have there been any studies related to this and death?
And death.
Death, yeah. Did you read Passages?
I haven't read that one. No.
Okay. So I take it you don't know any.
No, I don't know any. Well, isn't Google going to stop death? Heard that?
Well, that's true.
Yeah. So, is that a question? Yes. Yeah.
Can you say that if people, if you get near the black hole and time slows down,
Yeah.
does that actually slow down their chronological aging?
It does. Yeah, so you would go out to the black hole, and if it seems like a week for you, you would actually just age a week, even though everybody else on the Earth aged 1,000 years. Yeah.
But you would experience time in the same.
You would
rate
experience
yourself,
1 week,
so
yeah.
It's not like.
You would age a week, and you would experience a week. Everybody else would
Even an
experience 1,000 years.
atomic clock would slow down, right?
Yeah, yeah, exactly. The slowing down time of the circumstances is not just perception, it is reality. All clocks would slow down the same way if they're with you in your spaceship. Yeah.
So when
Yeah.
NASA decides to send something, they have to consider that whole movement issue that you're talking about, that if they, like
Oh.
sending a ship to Mars.
Oh, yeah.
They have to do a little bit of configuration.
Yeah, exactly. When you send a spacecraft to Mars, you don't send it to where it is now, you send it where it's going to be in 6 months, because that's generally how long it takes to get there. Yeah, that's true. Any other questions?
No more questions? I have tons, but don't want to bore you with any. Well, one thing, is this just a layman's response? I consider this type of stuff to be very similar to philosophy. Where is the line, see, that just might be me not understanding anything about physics, but do they overlap? I mean.
Yeah, I mean, there are people at Sac State who are in the philosophy department who do the philosophy of science. And that generally deals with questions of what is provable and what's not provable, what is the nature of reality, and so forth. And so there are certain areas of physics, and this also goes for quantum physics, for example, which deals with, is reality real, and are solid things actually solid, are they waves, and stuff like that. So there's a lot of overlap between some branches of physics and philosophy of science. But of course, when you get a PhD degree, that stands for Doctor of Philosophy. So originally, we were all philosophers, and we just sort of specialized really much into different areas of philosophy in that sense.